So, good morning, everyone. Thank you very much, Mike. Thank you all the colleagues from Waterloo and Toronto for the organization of this nice meeting. It's really a great pleasure to be part of this ICAP meeting and to finally meet again many friends and many colleagues. We were quite far apart in the recent years. So I'm Julien Laurat. I'm professor of physics at Sorbonne University in Paris. And I'm leading a research group in quantum optics and quantum information networks at Laboratoire Castor-Sprossel. So the focus of my talk today will be about one of our ongoing efforts to implement light matter interface, which are in single pass. And to do that, we combine nanoscale waveguides with cold atoms in the proximity. So before that, I will take this opportunity because we are still, we are a large community. We are at the beginning of the week, so we have a lot of time to discuss all together. So I want to take just a few minutes to give you a short overview of our group activities. So the first one, there is no atoms. So what we are working on is to develop capabilities to realize what we will call a quantum network, an heterogeneous quantum network. What we are going to see, or what we are seeing already in quantum technology, is a very large variety of devices, of platforms, of protocols. And it might be very soon a bottleneck for scaling up this quantum communication and quantum computation infrastructures. So you need to find ways to make quantum interconnects, and this work rely on hybrid entanglement of light, so what we did a few years ago, where you have entanglement between a single photon state on one side and Schrödinger cat state of the other side. So CV-DV hybrid entanglement of light. So since then, we have been leveraging this resource to make some useful protocol for heterogeneous networks, like hybrid entanglement swapping, to extend the distance when you can share this kind of entanglement. And one of the recent work we did, that was a PhD of Tom Darras, was to make a qubit encoding converter. So it's a kind of a black box, which is based on this hybrid entanglement, which is based on teleportation, with some Bell's state measurement in the middle, which is a hybrid one, combining single photon detection and homodyne conditioning. And you can start from any single photon qubit at the input and get a cat state qubit at the output. So you are mapping two block spheres, and you exchange the computational basis, and with a pretty large fidelity, which is beating all the classical benchmark you can have in this system. So let me go to the second effort we are pushing, and I'm getting closer to atoms, which is to develop quantum memories for local interconnects. Memory is a pivotal tool that you may use to synchronize resources, but also at large scale if you want to build a quantum repeater or a quantum internet facility. So what we have been focusing in my group over the recent year was to push a very important parameter, which is actually the name of the game if you look in terms of scalability, which is a storage and retrieval efficiency. So you take a photon, what is the probability to get a photon out of the memory? And this is the parameter which gives you a much better scaling in a quantum repeater scenario, for instance. So we have been working on that. The name of the game is the number of atoms, or more precisely, the optical depth you can get in this kind of system. And we developed this is a picture where you can see here a very elongated magneto-optical trap with centimeter-long atomic ensembles. We understood what we had to do to get very good storage and retrieval, changing the laser, working with some specific atomic transition. And we end up with demonstrating a 90% storage and retrieval efficiency with this setup. We did it with single photon. We can preserve the G2 below 0.1 in this experiment. And we even push it to making entanglement between two quantum memories, so mapping entanglement into and out two quantum memories with this kind of efficiency. And that will be the basis of future work in this Quantum Internet Alliance, which is one of the flagship projects in Europe to develop some quantum repeater capabilities. I come to the focus of my talk today, which is to make light matter interface in single pass, so which should be inherently very efficient, by combining atoms close to a nanoscale waveguide. And I would like to show you two platforms which are at very different levels of development. So the first one, which is an optical nanofiber, where you can have atoms which are weakly coupled, but you can have a large number of atoms weakly coupled to the optical nanofiber. And I will show you how in the recent years we have pushed this platform into the quantum regime with a few protocols. The second one I want to address, which is not at all at the same level of development, but which is bringing many promises for the field, is the use of slow-mode photonic-crystal waveguide. And I will show you what are the steps we are taking to build a new machine where we will be able to leverage this waveguide QED approach with photonic-crystal structures. So let me take one step back and come back to light-matter interaction. We all know that making a photon and an atom interact is pretty difficult due to the cross-section of your atom. So we know how to go wrong, either by strong focusing or by cavity QED, by enhancing the interaction by the number of round trips in your cavity. But we have seen over the last 10 years the emergence of a new research field, which is waveguide QED, and we heard a bit already this morning, which consists of taking benefit in a guided system of a strong transversal confinement of the light propagating inside the waveguide. And in that case, you put the atoms close to the waveguide in the evanescent field, and you can have a strong coupling between the atoms and the guided mode. And this coupling is given by two terms. The first one is a geometrical term. This is coming from the transversal confinement. And the second one is a group index. So if you can propagate the light slowly, you will increase also the coupling in your system. So waveguide QED has been studied in many systems. So we have seen very nice works in the microwave regime, for instance, using Transmon qubit. And also, and this is the talk, this is my topic today, using the optical frequency regime and coupling neutral atoms close to this kind of waveguide. We have seen many exciting proposals over the years. I just cite a few, realizing in this kind of system atomic mirrors and cavity QED based on these atomic mirrors, realizing quantum state engineering, and also that was a work by Anna Asenro-Garcia we heard this morning about memory exponential improvement by using the interference effect in this one-day chain of atoms. And also when you go to the nanoscale, you have a complex polarization structure, you have a strong longitudinal component, and then you can have an asymmetric decay in the decay. It can be symmetric or asymmetric, you can control that, and that's all the field of chiral quantum optics. So there was a proposal, for instance, of building chiral spin networks based on these properties. So many of the works which are presented here, at least part of them, they can be done with ensembles of atoms which are weakly coupled to a waveguide, and that will be the case for an optical nanofiber. But in this waveguide QED paradigm, we have another tool that we can leverage. You can, for instance, structure the waveguide. You can see here, so it's a propagating waveguide with a structuration. And then this structuration is going to change drastically the light propagation with guided modes and photonic band gaps. And these properties, they can be tailored, and they can change in a qualitative way and in a quantitative way, both of them, qualitatively and quantitatively, the light-matter interaction you will have for atom in the proximity. So let me give you the idea why you can reach new regime by using this kind of platforms. So let's say this is a dispersion relationship you get, so with a band gap. So close to the photonic band gap, you have a flat band here, what I call the band H. And then the group velocity will be very large. So the light will propagate slowly. So if you go close with an atomic frequency close to this band H, close to this photonic band gap, you will have an enhanced coupling of a single atom to the waveguide. And you can reach what I will call here a strong coupling to the guided mode. So what you can get in this case is an atomic ensemble of atoms where you can apply all what you know in light-matter interfaces in terms of quantum memory, in terms of DLCZ protocols, but also in a system where each atom will matter. So very strong non-linearity in single pass can be achieved in this system. But the atomic frequency can also be inside the photonic band gap. And if you do that, light cannot propagate, but you can have an evanescent field around each of the atoms. So you can define in this way an atom-photon bond state, which can be a very nice tool to induce some effective spin interaction between the atom, and with the unique properties to be tunable. So you can tune this distance either on a long range, infinite range, if the detuning is not too small and then the decay covers the whole atomic ensemble, or to the nearest neighbor if you are very far detuned from the bound edge. So this is opening many possibilities, these two regimes, and we have seen a wealth of theoretical proposals from quantum nonlinear optics to quantum simulation of spin models, and all that has been reviewed in this review of modern physics paper by Derek Chang and Jeff Kimber. The take-home message for me today is this one. So experiments are very far behind all these exciting opportunities in this structured waveguide QED field. And I will show you what are the steps we are taking to get closer to a machine where we can explore these possibilities. So let me go to the first setup I want to show you, an optical nanofiber. So where I can have an ensemble of atoms. So this is a lab, some light painting. We go into the chamber, and then inside the vacuum chamber, we put an optical nanofiber. So an optical nanofiber is below wavelength. It's 400 nanometers over a few millimeters in length. And we have a very strong evanescent field where we can put atoms in the vicinity. So we trap them in a dipole trap. We use for that a two-color evanescent field with blue detune and red detune light, and we can stabilize the trap in this way at a few hundred nanometers, 200 nanometers from the surface. And again, the coupling is pretty small. If you look this beta parameter, this Purcell factor is something like 10 to the minus 2, but you can have thousands of atoms working together. The first paper we did a few years ago in my group was to make an optical memory. I was coming from this field basically for many experiments, so the first one we did was to make a memory in this system, and realizing a proposal by Akuta 20 years ago. So the idea is to have a guided light into the nanofiber, which was at the single photon level, and then a control field, which is illuminating the whole sample from outside. And at that time, the atoms were not trapped in my group. We were just overlapping the nanofiber with the magneto-optical trap. So we did the first memory experiment, which was at the single photon level, which was the first important result. We were able to go to this single photon regime. With a few microseconds, we were studying in this paper also what were the limitations of this lifetime on the decay range, but of course the atoms were not trapped, so the transit time was one of the main limitations. And we were obtaining a storage and retrieval efficiency around 10%. You can see typically plot, which gives you the counts at the output, where you see some leakage, and when you switch on the control field again, you see some retrieval. So then, we wanted to use our atoms, which are now trapped along the waveguide in this optical lattice. So what we did was to make a collective entangled state, so trying to get an heralded collective excitation of the atomic ensemble, and being able to read it on demand as a single photon, but as a single photon into the waveguide. So to have a preferential coupling of this collective excitation with the guided mode. So that was reported in this paper 2 years ago. And the way to do it is the following. So we want to prepare a collective entangled state, and the method is well known in free space. We call that an emissive memory sometimes, but it's the Juan-Lukin-Sirac-Zoller protocol, the DLCZ protocol, which was a seminal way to go for quantum repeater architectures. But here we do that in a all-fibered configuration. So we start with this three-level system. All the atoms are here, and we send a right pulse, which is going to induce some spontaneous Raman scattering. And then if you detect a single photon into the guided mode here, you herald the creation of this spin flip. You don't know which one has been flipped among the thousands of atoms you are using. If everything works well, then when you read it out later on demand, you should get back a photon into the guided mode in the other direction. So it was very, at that time, it was not obvious that it will work because there is a lot of work in terms of filtering. We are working with a few milliwatts, up to 10 milliwatts of trapping light inside the fiber to get the trap on all the time. But at the same time, we are making single photon experiments. And it was not obvious also that the use of silica in this kind of system, for instance, will not induce some additional background, which will prevent us to go into this quantum regime. So there are many ways to characterize this system. I just want to show one, which is given an excitation. First, what is the probability to get the light into the fiber? So how preferential is this coupling? So you can measure the retrieval efficiency as a function of the excitation probability in the first stage of the protocol when you write the excitation. So if you excite it very weakly, it's too noisy, so you don't have actually an excitation, so this is why this guy is decreasing. If you excite a lot, then you are creating multi-photon components, so it's a kind of fake retrieval efficiency you get in your system. But in the middle, you have a kind of plateau, which should be a single excitation regime, and we got 25% retrieval efficiency into the fiber mode. 25 was pretty good result if you compare to free space experiment in single pass, where the values are typically from 40 to 50%, and we think in our case it was mostly limited by some polarization alignment. So then you want to check that indeed this regime is a single excitation, so you go into this regime, this is this green part here, and you measure the conditional G2, so the suppression of the two-photon component, and we were below 0.1 in this experiment. So that was the first demonstration of a collective integral state of a 1D atomic register. So it can be useful in terms of quantum networks, that can be a local node in this kind of architectures, but it can be seen also as an initialization stage. You create this collective integral state that you can read it out later on or use in a protocol as a starting point. So let me go to the third experiment I want to show you, which is the realization of a Bragg atomic mirror. So before, the distance between the atoms were, let's say, completely random relative to the atomic transition. It was the same, it was always the same, but it was random, it was non-commensurate with the atomic frequency wavelength. So what we did in this experiment was to use this trap atom and to adjust the distance between them. So why that? So I said each of the atoms is weakly coupled to the guided mode, but you will have, therefore, a small reflection. But if you put a good distance between them, lambda over 2, then all this small contribution will interfere in a constructive way, and then you will get a Bragg mirror as you get in a dielectric stack, we all know. So with this experiment, of course, we cannot put exactly lambda over 2 in our trapping. We will not be trapping anymore. So we had a very small mistake in the wavelength of trapping, which was below 0.1 or close to 0.1 nanometer. So then we were able to measure. I give you here the reflection and transmission. So you look at the blue curve, which is a reflection as a function of the probe detuning, and we had up to 70% reflection in this system. So 70% reflection in single pass with only 2,000 atoms. We came back to this experiment recently, and it was one of our main motivations to add now some dynamical control of the Bragg mirror. So we started from this Bragg configuration, and we added a EIT control in this system, and the control field now is guided. So you also benefit from this transverse confinement of the light into the waveguide. So this is a kind of spectroscopy you can get, where you see reflection and transmission. I don't want to comment. But if you choose a specific two-photon detuning, which also is related to the mistake we make between the distance between the atoms, what you get is this kind of plot. Without EIT, you get this large reflection in blue. And if you go to EIT, then you can get, instead of the reflection which is on the side now, you get a large transparency. So what you can try to do in this single-pass interface is really a directional router where you send a single photon. It's either transmitted or reflected. It's not just transmitted or scattered, but it's either transmitted or reflected in this system. So then you can characterize the typical number of photons you need in the control field to switch this transmission or this reflection, and we get these kind of numbers, a few thousand for the transmission and a few hundred for the reflection. So then we want to push further this, further down this number of photons in the system. And then you can do it with a 4-level key. So this is well known in quantum nonlinear optics. That was done, for instance, in this paper by Mike and in the group of Michel Lukin, with a hollow core fiber, where the transversal confinement is not as good as in the nanofiber. So now you have a control field, but you add also a switch field, and you will be looking the number of photons in the switch field to control the system. So you have to invert the logic you are using. So this is the kind of plot you give. Again, I will not comment them, but what I want to show is we are pushing the border closer to a lower number of photons. So here what you get is a switch with 30 photons. So we can switch the reflection in this system with only 30 photons, which is 1 to 2 orders of magnitude better than any single-pass system so far. And you can also switch the reflection. You can also find a sweet spot with the detuning on different protocols to have your system behave really like a directional router with an optimized contrast that resulted from a few weeks ago. And with something like 200 photons, we can make this directional router. So if you want all the details, all this work were done by Jérémy Berroy and Freddy Bray, and Jérémy is here, and he has a poster on Thursday on all these topics. Just to point out two theoretical papers, I would just flash them. One recently on extremely subradiant state in 1D chain, and that was a work with Alexandra Sheremet, and one work with Dima Kupriyanov, which was to start, so it's a theoretical paper, but to start from this capability to create a single collective excitation in our system, and then to put atomic Bragg mirror and changing the distance between this atomic Bragg mirror. And then we were studying the exchange of this excitation between the segments of the system. Okay, so we have a nice platform, the optical nanofiber, where we have been able to push now many capabilities into the quantum regime. But we also want now to leverage the other possibility in Waveguide QED, which to make a photonic-crystal structuration of the waveguide. So again, I want to keep a waveguide where the light can propagate. It's not a nanophotonic cavity that I will be using. So it's open these two parameters, these two regimes I said before, with linear and non-linear effect in the same system, and all this bandgap physics that we can study. So this is the kind of system we are going to do, actually. This is called a half W1. I will come back to that. But before going to these new protocols, we need to design these kind of structures to facilitate the loading. And we need to find also techniques to transport the atoms close to the surface, which has been a roadblock for the field so far. So we know a few experiments using this approach. One with quantum dots. This is all the work by the group of Peter Lodal, where you put quantum dot in this kind of systems, and then you can have a very, close to unity collection efficiency with a single emitter. And also the seminal work by Jeff Kimball at Caltech, using the alligator waveguide. And the alligator waveguide is a very specific corrugated bridge waveguide. So they have demonstrated some first capabilities in this system, including interaction around the band edge, but atoms were never trapped with the guided mode, as we can do with a nanofiber. So what we want to do in my group is to combine a bit these two approaches using 2D photonic crystal, so this is what we call a W1, where you remove a line of hole, and then you have a guided mode, which appear in the previous photonic band gap of the bulk. But there are 5 key requirements if you want to do that, which are very challenging. So you want a slow mode here, which is aligned with the atomic transition. You want a large fraction of the electric field outside of the structure to be able to interact efficiently with the atoms. But at the same time, you want to flatten the band. So it means it has to work with, to interact with your photonic crystal structure. So it's kind of contradictory challenges you have here. You want also to be able to have additional guided modes with low power. I mean, if you find that you make a trap with 100 milliwatt, it's never going to work. So you want to be sure that you are in the milliwatt regime. And finally, you should work as much as you can to facilitate the optical access close to this kind of structure. So we did all that. That's a collaboration with C2N in Paris, the group of Ariel Levenson and Kamel Benchek, and at Institut d'Optique, the group of Jean-Jacques Greffet and Christophe Sauvin. So we are using a very specific material, which is gallium indium phosphide for the field, and which has a very high refractive index, which is facilitating the design. We are optimizing the band flatness by doing some engineering of this structure. You can also see that given the sharp wall that we have here, we should have a facilitated optical access. And then we can still find guided mode for trapping. So all that was done by Adrien Bouscal. You see the fabrication here, I wanted to say. So all this engineering was done by Adrien Bouscal, who is here also, and he has a poster today on all this engineering of this kind of new waveguide. We are also studying some other kind of waveguide, because this dispersion relationship close to the band edge is pretty important. And here you can have a quartic dispersion with an asymmetric comb waveguide, and we also fabricated to see if it was possible to have this kind of suspended structure. Just to say something about trapping, again, trapping is very important. And you need to have a kind of systematic workflow. I mean, you are working on structure. You can discuss with Adrien about that. And when you are doing that, you want to be able to simulate in an efficient way your optical trap. So during the lockdown, basically, Jeremy and Adrien build this open source package, Nanotrapy, which takes any electric field distribution and can give you at the output the trap you will get, and you can change all the powers, all the combination of pins. The last point I want to show you is, so we need to develop this kind of nice structure. We are doing it now. You have seen fabrication. We are building also a new lab at Laboratoire Castres-Brossal to have this structure ready to put into it. But you also have a roadblock, which is how you put the atoms close enough from the structure to go into the guided modes. And that has been a roadblock. So it's not an issue with nanofiber. Nanofiber is very small. You put it into a magneto-optical trap, and then you can load the atoms. And this is why we are trapping atoms for years with optical nanofiber. But when you have the alligator waveguide, or the one we are developing, you have a large footprint, and it's not easy. So one strategy to do it is to use an optical tweezer. So you start from a few tenths of micrometer away, and then you focus the tweezer on the surface. This is a picture with the alligator waveguide, and you go closer and closer from the surface. But actually, there are two issues. From you have a limited axial confinement, because if you have a 1 micrometer wave, don't forget it's 3 micrometer in Rayleigh range. And the other issues are these reflections. And actually, if you make a simulation, so this is the surface of the waveguide, many atoms you start with, and you move the tweezer closer and closer to the surface. And what you see are many fringes, because you have a large index of refraction on the surface, very large reflection, so large contrast. And actually, at the end of the day, none of the atoms will end up here in the Z1 trap at λ/4 from the surface, which is the one you want to target. So there are ways to go around, which is to use higher order modes, like these radial P modes, like Argos P mode, where you have a GUI phase shift. And you can play with this GUI phase shift, which is this phase change when you go at the focus. So that was an idea we developed when I was, before the pandemic, in sabbatical, working back with Jeff and with Jean-Baptiste Béguin, to make a bright optical tweezer with a reduced volume, but most importantly, reducing a lot, thanks to this rapid change of the GUI phase, all this reflection on the surface. So this is the same simulation, where you see you can have a kind of bullet of atoms. They are all moving together. The fringes are much more limited. And if you make the simulation to the end, what you find is that this technique should enable to get 60% of the atoms at the end in the Z1 trap, while if you make the same calculation with a Gaussian tweezer, you end up with basically below 1%, so nothing, and this is what happened on the experiment. So it can be a game changer, and we are currently doing it, implementing that in the lab to show that we can transport atoms. So let me conclude. I wanted to show you today two platforms for Waveguide QED, which are not at all at the same level of development again. The optical nanofiber with many atoms coupled weakly to this guided mode, and we are pushing this field into the quantum regime. And the second one, where we can have a limited number of atoms, but coupled to this structure waveguide with all this possibility of quantum nonlinear optics and also quantum simulation via this atom-photon bond state. So let me thank all my co-workers. You can meet them again during the poster sessions. And also Alban Hervois, who is a new associate professor in my group, leading all these activities with me now. And you can meet him. He's also here for the whole week. I will stop here. Thank you.
Thank you so much for the great talk. Let's thank the speaker. We are running just a little behind, so we have time for maybe a couple of questions, especially short ones. Short ones are preferred.
Yeah, thank you. I was wondering, could you go back to your slide that shows the full-level EIT scheme? You see it as a switch to control transmission and reflection. Oh, sorry. Yeah, this one. Could you go to the one with the table? Yeah, I was wondering why in this table that with and without the switch, the overall, like, how to say, if you sum these two together, is a factor of 2 difference. What limits the performance on that? It's like without the switch, the total kind of 90 you can get is like maybe 50%, but with switch, it's only 25%.
So you mean the difference between the transmission and reflection, basically?
Yeah, if you adding them together, the efficiency.
Well, if you look at the spectroscopy at the beginning, I was showing already at the beginning to start with the transmission and the reflection, they were not at the same level. I mean, with the EIT, we were pushing the transparency much higher than the reflection we can get in the system. So I believe this is still coming from that at this point. It's one part of the answer. The second part of the answer is this is a sweet spot. So we are trying to make all that work together, so you have to take into account the whole detuning. And of course, you want a pretty good contrast between transmission reflection and transmission reflection in both cases. So we found the best parameter to do that. There is a third point to my answer. You can improve these numbers if you go closer to resonance for the trapping of the atoms. As I said, we are lambda over 2 plus a delta lambda, and that is something you have to manage, and which is degrading the performances. So we went as close as 0.1 nanometer, which is still okay in terms of filtering. If you go closer, it begins to be difficult, and then you need to find other way, like blue trap, to go exactly at lambda over 2, which can be one research direction.
Thank you.
So this concerns the memory and retrieval when you had the DLCZ protocol with the atoms on the fiber, and you said you got 25%, which is a nice number, but you said it was limited in part by problems with the polarization control. But what I'm wondering is, what sets the limit? That is, what's the theoretical limit? I presume it has partly to do with how close you trap the atoms to the fiber, but of course you can't get too close because, well, you know why. And and of course there's always the radiation into free space, which is what you're trying to fight against. So what I'm wondering is, what are the ultimate limitations? And the other thing is, I didn't really understand whether the DLCZ protocol, that is, whether the phasing improved that that coupling compared to what gets radiated into free space.
Okay. So if you do a DLCZ experiment in free space, so it's very sensitive to the polarization you will be using, depending on the atoms you are using, if you use Zeeman pumping or not. So we know that in our system it should be this polarization and this polarization to be optimal, but then you have to control the polarization over the whole fiber, which we do pretty well, but there are still some inhomogeneity. So we believe going this 25 to 30 or 40% was coming from this alignment of the fiber. And by the way, we changed the fiber after doing this experiment because it was a bit crappy and we had some polarization issues. The limiting factor for the DLCZ is like, I would say, the optical memory experiment. What you want is many spins to work together. So the optical thickness will be the limiting factor. So you are seeing in the memory experiment in free space, we can get 90% storage and retrieval into single mode fiber, but we are using an OD of 500. So if you are able to push in a DLCZ experiment the OD, you should be also able to improve the retrieval efficiency. So here with more atoms, we should be able, here the OD which was used was around 50, so we should get a little bit more than what I said. This is why there is this issue of polarization, but this is a typical number. I fought for that for years, actually, in my lab, because I still want to make an efficient DLCZ with a free space atomic ensemble without a cavity. So what you do a very elongated MOT, like I do for the memory. But no, it doesn't work. It doesn't work because you always put an angle between your right and quantum field 1 and field 2. Or exactly like in the EIT experiment, you put an angle between the control field and the signal field, just for filtering issue. If they are collinear, there are no way to get a very good signal-to-noise ratio. In EIT, you write in this direction, you read in this direction. So you have no issue due to this angle, for instance, on the splitting in the ground state. If you do it with a large atomic ensemble, which is centimeter long in our case, then this angle plus the fact that you have a splitting in the ground state will become a phase matching issue. So we should be able to make a very large OD in a very small sample. And that will largely improve the efficiency.
So are you saying that, okay.
My apologies for
Let's take a
cutting you
coffee
off, but
together.
yeah. So yeah, so this concludes the last talk
Thank you very much.
of the first morning session. So let's thank the speaker and all the speakers for the session.